Okay, then I'll just jump in. Okay, so hi everybody in the void and wherever you are. So I'm the speaker for today, and I'm going to tell you a little bit about some of our recent work done by a couple of very good postdocs, primarily at the Max Planck Institute for Microstructure Physics in Halle. And the title of the talk is The Realization of the Field-Free Josephson Diode. Then I will explain what I mean by the Josephson diode as we go. And I'm also going to give a little bit of background to lead up to this. So, one doesn't work. Okay. So, in terms of an outline, first I'm going to very briefly just describe a little bit about how this research looks like. Not everybody is familiar with the sort of combination of material science, solid state chemistry, condensed matter physics, and then device physics. So just a little bit of an overview. Then I'm going to do a very brief background into superconductivity, primarily just a couple things that we're going to rely on for the effects that we show here, particularly the zero resistance and Cooper pairs. And then we're going to talk a little bit about the fact that somebody has seen a sort of a diode effect in a bulk superconductor through a mechanism known as Magnetochiral Anisotropy, which I'll try to explain briefly. And then we're going to go into Josephson junctions, why they're so important, how they came about, the myth of Josephson's homework problem, which I think is a fun story, and of course, you know, his so-named effects, why they've, you know, revolutionized various technologies in the 21st century and are very critical to developing technologies. And what I think is, I'm going to call sort of the next generation Josephson junction, and I'm calling it quantum material Josephson junctions, which is one of the main thrusts of my research and the new group that we'll be starting very shortly here in Delft, actually, where we will be moving. So, thanks. Yeah. So, basically, in a nutshell, the concept there is to marry quantum materials and Josephson junctions. Because of how Josephson junctions are structured, there is a barrier material that classically has been either a simple insulator or other types of, again, relatively classical materials, not quantum materials. And the inherent properties of quantum materials might modulate the Josephson behavior in new ways. And that's exactly what we're going to show in terms of the Josephson diode and how we achieved this. And so I'll talk a little bit about niobium through brominate and then get into our, you know, new content. So the research flow. So in general, I think like any science, this starts off with developing the idea. So that's sure a lot of, you know, sitting around, drinking coffee and thinking, but it very much involves a lot of interaction, and that's the type of research we like to do with our colleagues, particularly our theoretical colleagues, like hopefully Anton in the near future. You know, a lot of discussion and marrying together interdisciplinary concepts. So once you come up with a sort of an idea of a direction to maybe an effect to try to see, we do the bulk material exploration. So that means really getting your furnace out and, you know, grinding up some material, making a sealed quartz ampule, sticking it inside, you know, one of these types of either a muffle oven or tube furnace, heating it up, cooling it down, cycling, and then actually trying to grow those crystals, connecting leads to them and measuring the properties. And then, you know, that feeds back with the theorists, depending on what you see and what you understand. From there, what we also do, particularly for the layered materials that are so popular nowadays, that can be exfoliated so that you can take out single or few layers at a time and sort of stamp them on top of each other, we create devices, something like this, a very simple one, where this is a flake. It's just like, I think, 50 nanometers thick and, you know, maybe a micron or so wide and a few microns long. And it's a beautiful, tiny piece of a crystal. And we are able to then pattern electrodes on it in various forms and make devices and sometimes measure properties that you can't measure so easily in the bulk, which is exactly what we're doing today, where we induced superconductivity and made a Josephson junction. It's not so easy to do that in a bulk crystal or of a several millimeter sample. And then we can, you know, stick it in things like our dilution fridge and measure down to super low temperatures. So all of this works very intimately with our theoretical colleagues. We're primarily an experimental group, although we dabble, but we lean heavily on our friends. That's something I'm going to repeat many times as we go on. You know, I get by with a little help from my friends. I get by with a lot of help from my friends, actually. But I like that, and together we can do lots of very interesting stuff. So, again, brief background into superconductivity. So Kamerlingh Onnes, who I believe was also from the Netherlands, or at least ended up at least in Leiden, was the first to report superconductivity back in 1911, where he was measuring mercury and found that about 4 or so Kelvin, the resistivity abruptly dropped by several orders of magnitude to basically the limit of his measuring ability at that time. So this is known as superconductivity, where you have a truly zero resistance. There's a few other effects that come along with it, known as the Meissner effect and whatnot, but we're not going to get into that today. The main thing to remember is that below a critical temperature, you suddenly lose your resistance. And it's a fundamentally fascinating concept that has been, I think it's resulted in like 4 Nobel Prizes over the years in various forms. And it took a long time to explain. It wasn't until the 50s, the 50s, that BCS theory came out to at least explain the original superconductivity. And it wasn't until the 80s that high TC superconductivity was found, which is to this day not fully explained. So this is a very important and interesting field in condensed matter physics and in physics as a whole. And as to this day considered one of the great mysteries is how does it work, especially for, again, the high TC superconductors, and how do we make an ambient condition one? So they're fundamentally fascinating. They're important technologically. This is how we make big magnetic fields nowadays most of the time. It's also how a lot of ultrasensitive sensors work, which again, I'll talk about when we get to Josephson junctions. And just because I think it's super cool, we also levitate trains this way. The Maglev trains, like I think it's most famously running in Japan. It's literally floating a train, taking advantage of flux pinning, and is able to, you know, travel with much lower friction, just air, and go very fast, basically. So there's a lot of cool Star Trek-y like science related to superconductivity. So it's a very interesting place to research. Now, one of the important things about how it works, especially like I said, the type 1 and BCS superconductors, is that we know how you form Cooper pairs. Cooper pairs being pairs of electrons. So normally you think of an electron and other electrons flying around inside a crystal, doing their own thing, basically, and certainly not being attracted to one another. They normally repel each other and scatter off of each other, or phonons and things like that. But below a certain temperature in certain materials, kind of essentially as shown in this very cute cartoon here from God knows how long ago, you can have a electron, as it flies by, displace a locally, like let's say the positively charged nucleus due to the Coulomb force, and that displaced nucleus then has an effect on the electric field it puts out, which another innocent bystander electron would notice. And so that it then gets shifted. And so through the mediation of this, you know, exchange, the first electron actually attracts the second electron. And so they're paired, which is weird to think about. You normally don't think about electron and attraction. You think only about electron repulsion. So this is the glue, the mechanism for Cooper pairs and BCS superconductors. Again, in high TC, to this day, we don't exactly know how what really the glue is. So that's a whole very fun field of research that we're not going to talk about. But the main takeaway is that the pair of electrons is not acting like a single electron anymore. It's not a fermion, it's now a boson. And so all of these pairs, the Cooper pairs, can occupy the same ground state, and hence you can get superconductivity because they're able to travel without resistance without scattering off of anything, because it takes a certain amount of energy, larger than the condensate energy, to scatter that in this paired object. So importantly, and this is the really important one that I just want everybody to remember, there are a few ways to break a superconductor. Obviously, you can go up in temperature. Like I said, this happens below a certain temperature. Basically, when the mediating nuclei stop wiggling so much, they essentially locally freeze, so that the attraction is greater than the thermal fluctuation. But also, you can break the superconductivity by putting too much current. So that's known as the critical current through your superconductor. So the critical current is important. Now, normally, superconductivity is reciprocal, as in, if it superconducts to the left, it'll superconduct to the right. That's what you'd expect for basically any material. But very recently, it was shown by Ando and others in Nature, and back in just last year, actually, for the first time, that they were able to make a bulk material, or any material really. It happened to be a bulk material that superconducted in one direction, as in it was the electrons scattered with a finite resistance along, let's say, to the right, but Cooper pairs traveled to the left. Now, this was a thin film, a repeating thin film of niobium, tantalum, and vanadium that was like 120 nanometers thick. And they saw this delta, they essentially saw a delta I, as in the critical current to the right was not the same as the critical current to the left. But they only saw that with a magnetic field. And that's very important, because this entire mechanism was based on something called Magnetochiral Anisotropy, which we'll talk about in a second. But the important thing is that the critical current dependence was anti-symmetric with the magnetic field. So what is Magnetochiral Anisotropy? Basically, you have to have, let's imagine a material, so this cube or whatever, that breaks both time reversal and inversion symmetry. The usual relations are up here. So if you have that, and I'm going to play a little fast and loose with my directions, so just bear with me, but if we imagine, kx along this direction, and we imagine that there was in this material some real space inversion symmetry breaking action. So for purposes of this, let's say Rashba spin orbit interaction. Let's say it was along the z-axis, and then you would apply a magnetic field to break time reversal symmetry. So this one broke inversion. Now we're going to break time reversal along the y direction. If we imagine, two electrons in here, the electron at plus k is not the same as the electron at minus k, because they can have different spin orientations, either aligned parallel or anti-parallel with the magnetic field. And that will result essentially in a energetic difference between, again, the plus k and minus k electrons, which will then result in a difference in critical current for let's say, positive x versus minus x. But again, that's only true if the magnetic field is on, because again, this whole system works by both breaking time reversal and inversion. So this is one route to non-reciprocal transport, to making, right not equal to left. But that's not what we're going to be using today, but it's important to know that this exists. Okay, so another direction to ask, rather than in bulk superconductors, is to ask about Josephson junctions. So we'll talk in a second about what that is. So it started, oh, did my computer freeze? And my mouse froze, okay. Whoa, okay, 1 second, sorry. No idea what happened. The whole presentation crashed. I'm sorry. Let me reload it here. Okay. Let's see, we were just about to start with Josephson Junction. Okay. Do people, no, you don't see anything yet, right? How about now? We're back? Good. Okay. I have no idea what happened, so sorry about that. Now, what I was saying, Josephson Junction. So, this all started with Brian Josephson. He was 22 years old, actually, in 1962. And he wrote down what happens if you take two superconductors and sandwich them across a non-superconductor. Now, in his original work, he was asking about an insulating barrier, but as we'll mention, that's not necessarily a requirement. But yeah, he realized and wrote down his relations that you would have a spontaneous DC current across this this junction. Now, the fun part of the story is that, and the myth is that this calculation was actually part of a homework assignment by another very, very famous Nobel laureate, P.W. Anderson. Now, as compelling as that would, we would love that to be, apparently the truth, as explained by Josephson himself, actually, is not quite as fascinating. But it was actually the other legend, Pippard, who drew his attention to tunneling experiments about superconductivity. And Anderson entered the story by basically guiding Josephson towards thinking about symmetry breaking. And based on that, he did his work. Now, fine, it wasn't necessarily a real homework assignment, but he was 22 years old. So, and he won the Nobel Prize in 1972, just 10 years later. So I think, it's quite compelling for any graduate student in the audience, I think, to maybe, if you have an interesting idea or an interesting question, regardless of whether a super genius, has guided you to do this, don't think that, oh, only another super genius can solve it. Maybe you're the super genius. You don't know. So, how does this work? So what is a Joseon junction? It's basically where you have two superconductors disconnected, or weakly connected is actually the term, by either a insulating barrier, a normal metal, a constriction, a point contact, some reason to basically have you can think about two branches separated by something that the wave functions of the two branches have to tunnel through. So here we're going to think about the Cooper pairs wave functions. Now, there's a whole lot of literature you can read about this stuff, so I'm not going to go into it in too much detail because I think it's also pretty common knowledge now at this point. But the takeaways, of course, were the main Josephson relations, where one, you have a sinusoidal dependence of the current depending on the phase difference between the two superconductors, and that at a constant voltage, you'll actually have the current ringing. That would be the AC Josephson effect. And you can make these things in either planar or vertical junction. So across a barrier material, literally above and below, or in a plane. Now, in a plane, typically these lengths are much longer. You're limited by your, for example, E-beam lithography resolution. So at the minimum, this is typically like maybe 50, 80 nanometers long. Now, it's hard to tunnel a superconductor or a Cooper pairs across a good insulator for 80 nanometers. It should just die. The wave function should basically decay completely before it reaches the other side, as our picture shows. So this is much more commonly seen with metallic barriers or in very specific types of fabrication, the famous aluminum oxide aluminum junction, but that's made in a special way. So it's able to make a very short channel that is not otherwise easily achievable. Now, with an insulating barrier, more typically easier approach is to go up and down, especially if you can make a very thin barrier by utilizing layered materials that, like I said, we can exfoliate them and grab just a couple layers at a time. So again, the channel length in the vertical JJ, and from now on, I'm going to refer to Joseon junctions as JJs just to speed things up. So the vertical JJ can have a much shorter channel length, and so you can use a good insulator. Now, there's a couple important things also to remember a couple other important effects. The first is the smoking gun of having a Josephson junction, is the current versus phase relation. So basically, like we said, the current is dependent on the phase difference between the two superconductors, and the phase difference can be modulated by the magnetic field. So through substitution, basically, you can measure the critical current as modulated by the magnetic field, and it takes on this form, which is exactly the single slit diffraction form. And so it actually looks like that. So if you have a junction and you want to see if it's really a Josephson junction, one of the most important experiments to do is to measure the critical current versus magnetic field dependence and see if you have basically a single slit diffraction, so a sinusoidal dependence in roughly a 1/b envelope. And this is important because the entire junction is very, very sensitive to the magnetic flux through the junction. And entertainingly, even more sensitive than one junction, maybe kind of obviously, is two junctions, for example, in parallel. So this is the squid, which is two Josephson junctions connected in parallel, and it's exactly analogous, as you'd expect, to a double slit diffraction experiment. So you get a faster oscillation that's, again, more sensitive to very, very small flux through, this time, not the JJ itself, but through the area defined by the loop of the two JJs. Now, how sensitive is this? Like, it's incredibly sensitive, down to, 10 to the minus 15 Tesla, for example. That's literally less than the human brain's magnetic field. So this is the basis for things like MRI. This is why Josephson junctions are very important. Well, one reason. Frankly, they're actually quite ubiquitous in a lot of important modern technology, literally from dark matter detectors. So this is a schematic of ADMX, the axion dark matter experiment. Geologists use it to basically try to detect the different types of minerals as in the ground, particularly during oil speculation, or whatever the word is when they drill looking for oil. Because different types of minerals tend to be around oil deposits, so they can try to find it that way. Again, like I said, it's the basis for one of the most important modern medical imaging devices. And in fact, JJs are used now in, I think the people have heard of this company, D-Wave, that makes these rapid single flux quantum computer chips that can operate at very, very high frequencies. So Josephson junctions are even, reaching commercialization in certain types of computation. And of course, because this is inherently a, quantum coherence phenomenon, right? The two branches, the wave functions are locked together. This is the basis for superconducting qubits. So all three types, for example, that are maybe the most popular, the charge, the flux, and the phase qubits, are actually based on JJs. And at this time, I think for the foreseeable future, superconducting qubits are probably going to continue to be maybe the most important route towards reaching higher number of qubit quantum computers. So JJs are very important. I hope I've convinced you of that for 21st century technology. So now to the really new stuff and the next iteration. So this is, what I'm calling quantum material JJ, so QM-JJ. So basically, what the hell is a quantum material? It depends who you ask, frankly. I think I like this definition the best. It's basically any material that cannot be best described, or is not best described, using classical particles or computations. So, there's a laundry list of materials nowadays that we would say have a, quantum phenomena, or that manifest quantum phenomena. So it's, topological materials certainly fall under this category. Spin liquids, certain ferroelectrics, certain magnetoelectrics, obviously superconductors, as we just talked about, strongly correlated materials, anything with the word quantum in it should be a quantum material. So the point is, there are these materials that have intrinsically interesting properties that if you stick them in between two superconductors as the barrier, their intrinsic properties might modulate the coupling of the wave functions across the two superconductors in non-trivial ways, in new ways, rather than the classical simple insulator barrier. So this is not, just pure pie in the sky stuff. For example, this has been seen at least once already in what's known as the asymmetric Josephson effect. The idea there was that you have, again, your two superconductors and a barrier material in between that was a topological material. So it had edge or surface states or hinge states, whatever, as well as the bulk states. And, the superconductivity across this barrier is mediated by all the metallic states available, including those edges and surfaces. Now, if you happen to be breaking inversion symmetry, then it's possible that you unlock let's say the top and bottom surfaces in terms of having the same Fermi velocities. It's no longer required. Now, exactly this scenario was seen in one of my favorite materials, tungsten ditelluride. So it is an inversion symmetry breaking topological semimetal. It was known as maybe the first type 2 Weil semimetal. Nowadays, it's known also as a higher order topological semimetal. It does everything. Somebody's talking about it as an excitonic insulator now, what have you. The point is, it breaks inversion symmetry and it has these localized conducting states. And pretty much as the theory expected, you can end up with a modulation to the Josephson effect, particularly that sinusoidal relationship isn't sinusoidal. It ends up being more like a sawtooth in the current versus phase, and that's pretty close to what was observed. So this is an example of a quantum material, in this case a topological material, acting as the barrier and making a sort of a new Josephson effect, or at least a modulated Josephson effect. I don't want to offend Josephson. So where else can this sort of logic take us? And this is where my fun starts, I think. So, I like to think about materials, wacky materials, and what properties they might have and how those properties might play together if I combine other properties with them. So smash, multiple phenomena together, see if you get emergent properties, right? So a material that a good friend of mine, Tyrel McQueen, had first investigated over at Johns Hopkins, and now it's two materials, it's a family, niobium-3 chlorinate and niobium-3 brominate. So they are layered materials. So that's the first checkbox. You can see you have nice layers of niobium in this case, at low temperature, they look to form these little trimers, but an otherwise pretty much hexagonal net stacked on top of each other. Niobium halide layers with a van der Waals gap. So they're really nicely layered and presumably very exfoliatable. Now, aside from that, they have something interesting going on in terms of whether they're cluster magnets or not. What's happening with the magnetism is not entirely known, but there's some sort of magnetic to non-magnetic transition around 90 Kelvin. So at low temperature, it looks to be non-magnetic. Okay. And it was predicted by Bernavig and friends to be a topological insulator, actually. It does not appear to be, but it was proposed that maybe it could be depending on the correlation strength. And in the monolayer, other people predicted that it should be, one of these 2D ferromagnets. So it's an interesting material and family to go hunting around in. So we did that. And like I said, it's very exfoliatable. You can see its interlayer traction energy is, less than maybe graphene. So it's really a nice material. And it's also quite stable in terms of atmospheric degradation. So it's a good starting point. So we started with some basic investigations and we, made our sandwiches. Not superconducting, we started with some basic transport exploration. And we found that one, it is easy to make devices. And very happily, odd numbers of layers break inversion. So it's a 6-layer repetition of the unit cell and they stack slightly off each other. So if you grab an odd number of layers, the stacking is not inversion symmetric. So you can, while the whole compound, the bulk compound, is inversion symmetric, if we take our exfoliated flake down to an odd number of layers, like let's say 3 layers which we will do in the next slide, then you can break inversion. Now, in terms of our general bulk exploration, we found something very surprising in that as you made this thing, oh, it's kind of low resolution. Well, it's hard to read here, but basically as you go thinner, the conductivity increases, which is not normal. That is unusual. It's sometimes been seen in things that have, for example, surface states. But it's also sometimes seen basically in things that have multiple conductive channels for various reasons. But we did, we wrote this paper where we found that this behavior was intrinsic. So all of this got us thinking that, boy, this material should be fun to make Joseon Junction out of. But the chlorinate is actually quite insulating, too insulating. It was difficult to make that into JJ, to actually get superconductivity, like I said, to tunnel across the barrier between the two electrodes. If you have too big of an insulating gap, you decay. Your Cooper pair decays, or the wave function decays. However, brominate, the cousin of chlorinate, now here's a little classic solid state chemistry. Basically, as you go a heavier element down your row, you have orbitals extended out further in space, greater dispersion. Long story short is that you get a smaller band gap. So the brominate is kind of the more friendly cousin of the chlorinate, and it does indeed have a smaller band gap and is actually even easier to exfoliate. So, after trying a little bit, we gave up on the chlorinate and said, let's go try the brominate. And that's where the fun really started. So we ended up trying to make this type of stack, a vertical JJ, 3 layers, an odd number of layers of niobium bromide, sandwiched between 2 normal superconductors, niobium diselenide. Well, I say normal, but type 2. The point is, there is not that special superconductors. It's not like a time reversal symmetry breaking superconductor. It's a relatively normal superconductor, but NBSE2 is also a layered material. So we were able to basically make ourselves a sandwich. We took our wafer, we put an underneath layer of NBSE2, then we put our 3 layers of niobium-3 brominate, then we put a top layer of NBSE2, and then we, capped it with some HBN. So everything was all nicely protected from air and all of that. So very clean devices. And we got it to superconduct. We were actually able to, tunnel across. So that was the big win, and that was very fun. The device critical temperature was almost 6.5 Kelvin. So actually relatively close to the TC of the niobium diselenide itself. And we found that when you transition below the superconducting critical temperature, you start to see a nonlinear IV. Now it's hard to see in this blue line, which is a 6 Kelvin, but if you have, eagle eyes, you can sort of see it. But obviously you can very clearly see it in the low temperature data. And there was a lot of hysteresis as well. So we're going to talk about these characteristics in a minute, but the hysteresis is as expected because if you look at this, it's basically a parallel plate capacitor, right? We have 2 metals, superconductors separated by an insulator. So you expect to have a capacitance. And if you have a capacitance, you expect to have a hysteresis. So that wasn't too surprising. What was really surprising is, okay, so this is a fun game actually. So this is the IV sweep done at 20 millikelvin. And I like to play this game of asking, in a real talk, I ask the audience to raise hands and see, do you see anything odd about this sweep? Now, importantly, the positive sweep, as in the clockwise, is exactly the same as the counterclockwise. So positive is starting from 0, is going to the right, up, left, down, like that. And a negative sweep is literally the inverse of this. So if you look really closely, as my postdoc Heng did, you can maybe notice that this is not the inverse of this. It's just barely wider than this. Now, I thought, my postdoc came to me and showed me this excitedly, and like I think any good PhD advisor, I immediately crushed his hopes and dreams, right? I said, no, this is nonsense. It's definitely an artifact. Here's 5 reasons. It's It's wrong. If you really believe it, go do it again, and then do it again, and then make it bigger, and then come back and talk to me. And like, you know, any very good scientist, Heng went away like a dog with a bone and did exactly that. And, you know, came back and showed me this plot and many more plots like it, where he went ahead for the sake of my eyes and did map the inversion of this loop onto the negative quadrant onto the positive quadrant. So let's take a moment and just understand this. So the 0 to p and p to 0, what that means is sweeping up from 0 to positive, then positive back down to 0. And the 0 to n and n to 0 is sweeping, the absolute values are shown here, from 0 to negative, and then negative back to 0. So the dotted line matches, so yeah, the dotted line is shows the hysteresis, the return for its corresponding solid line. So the same colors are the same quadrant. The different colors are the different quadrants. What's very important is that the yellow line and the green line, as in IC plus and the absolute value of IC minus, so IC plus, the critical current to break superconductivity in the positive direction, and the critical current to break superconductivity in the negative direction, are clearly not the same. There's a pretty reasonable size gap. There's a delta IC between these two. And the critical current with negative voltage is greater than the critical current with positive voltage. So, you know, now that's really something that was very clear. And so, you know, again, to say, is this really real? Then we should be able to do something very simple. We should be able to say, okay, let's take a current value. So this is current source experiment. Sorry if I didn't make that clear. So let's apply a current value in between IC plus and absolute value of IC minus. So greater than IC plus, but less than IC minus. So like maybe just below 8. And flip it, you know, apply a square wave, and we should see it only, you know, superconduct in one direction and not the other. So Heng did that. He applied a 7.9 microamp, which is in between IC plus and IC minus. And so this is the application. This is the applied wave. And you can, this is IC plus, you know, this is IC minus. And you see on the positive side, we have a measurable voltage, as in a finite resistance. Whereas when we apply the negative current of the exact same magnitude, just a different sign, well, you don't. It's superconducting. And back and forth and back and forth. So we really are rectifying half of this excitation. So it really is, again, like a diode. It's superconducting in just the one direction when we choose this applied current carefully. Now this is 20 millikelvin, and the rectification ratio is really high because, you know, I mean, it's superconducting to not superconducting. So it's at least 10 to the 4, basically. But the other fun thing we just decided to check, just to be sure, is, you know, we sped it up a little bit because we didn't want to run this for a lifetime. And ran, you know, 10,000 cycles and just watched it. You know, did we have so-called punch-through error, where when we flip the sign, again, applying the same magnitude, in this case, positive current, do we accidentally end up in a superconducting regime again? As in, do we punch through that delta IC because of instability, because it's wiggling around, because of heating, because, you know, Joule heating or whatever? And the nice thing is, no, we don't. It really just works. It follows the applied wave. For again, it's not that many, but it proves the point. 10,000 cycles, not a single punch through error. So it's very stable at that temperature. Now, of course, as we increase temperature, get closer to TC, this changes. So at 0.9 Kelvin, so nearly a Kelvin, this is still working exactly as expected, as it's described before. But at about 4 Kelvin, so quite a high temperature now, and the important thing is, at this temperature, the hysteresis, you might notice, is almost completely gone. Again, the hysteresis is between a solid line and its corresponding dotted line. The delta IC is between the two solid lines. So you see there's still a delta between the two solid lines, but there's almost no difference between the solid and dotted lines. So the hysteresis is pretty much gone. The delta IC still exists though, but there's starting to be this sort of punch through error. You see the instability of the measured voltage when we flip sign. Sometimes we do see it appear to superconduct. So it's not as stable as you go up in temperature, but you know, I think that's expected because of the magnitude of thermal fluctuation of noise current, which we'll describe in a minute. But being, you know, around 2 Kelvin, this still works just fine. This is at 4 Kelvin where it starts to break. I think as long as you're above 2 Kelvin, that's already pretty good. And we can go from the under-damped regime to the intermediate damped regime, and the whole thing still works, which is important for some applications I'll talk about later. So the next question was, is this really magnetic field free? So remember what I mentioned in the very beginning with magnetochiral anisotropy and the bulk effect, that is purely dependent upon a magnetic field. You have to have it. We apparently seem to do all this with zero field. So is that really true though? You know, could there be remnant field? You know, the instruments always have their own problems. So you sweep field. Now just to make it clear, this is a heck of a lot of work actually. So you know, I have to say that Heng did a phenomenal job, because each one of these points is one of these sweeps. So one of these sweeps is a vertical slice in this sort of map. So yeah, to get this sort of data, you take a lot of these. And you notice something very interesting. The IC plus and IC minus are symmetric in terms of their suppression with magnetic field. And they're both maximized actually at zero field. It's just that the IC minus is maximized more. It's just larger. And this whole effect appears to turn on for some reason about below 35 millitesla. And we don't have an answer for that yet. So this is an interesting open question. What's going on at that magnetic field? But compared to finish the comparison with the magnetochiral anisotropy route, this is how the magnetic field dependence of IC looks like. Exactly like we derived earlier, precisely at zero magnetic field, you must have a zero delta IC. It can exist. In fact, it's maximized with a small magnetic field that also then gets suppressed, but the two I plus and I minus cross at B equals 0. So you can just see very clearly it's not the same. So the Josephson diode is definitely not the same mechanism. Okay, but what else is going on? Like I said, we have the whole effect turns on around 35 millitesla, and then it stays relatively constant. We have a delta IC of maybe 0.4, 0.5 microamps, which is pretty large, considering the IC itself is on the order of just a few microamps also, and it stays relatively flat. So again, what's happening at 35 millitesla? This is something that's an open question that I think is material intrinsic, but I'm not going to talk about it too much today because there's other things we've got to get to. So, like I said before, is it just a junction, or is it really a Josephson junction? Is it really a Josephson diode? Do we have the Josephson coupling? Well, here's the you know, it's a little dirty, but it's pretty close to a modified Fraunhofer pattern. Certainly we see the expected maximum at zero field, and you know, a roughly sinusoidal, a damped sine decay with increasing field. So yes, it's really, we do have Josephson coupling between the electrodes across this, you know, niobium 3-chlorinate barrier. And does it really break inversion symmetry? Again, yes. Both intrinsically, the 3-layer niobium 3-chlorinate brominate breaks inversion. And then also we arbitrarily twisted the electrodes on the top and bottom. So the whole stack really should break inversion. And to prove it, the second harmonic resistance when entering and exiting superconductivity are of opposite sign, exactly as you'd expect. So yeah, it is breaking inversion symmetry, it is Josephson coupling, and it is a diode effect. So, you know, Josephson diode. So how can we understand this non-reciprocal behavior? Again, without an applied magnetic field. So very quickly, you know, phenomenologically, there's the resistive and capacitively shunted model. You can think about a Joseon junction in terms of pieces, circuit components. So there's the supercurrent. There's if you're not actually going to zero in terms of your resistivity, if you just have a partial drop, then you have a normal current. There's again, we have a capacitance for sure. So there's a displacement current. And then of course there's always noise. So let's just take each of these in piecemeal. First off, the noise current. Like I said before, it's just small. At the temperatures we're at, in general, the noise current is certainly dominated by thermal fluctuation. Your kBT is just on the order of a nanoamp, whereas our delta IC is on the order of microamps. So, it's just not the main driver. So in principle, though, any of these other three, if they were behaving in a non-reciprocal fashion, the total behavior could also be non-reciprocal. So, so if we drop the noise current, the total current simplifies to the usual formula. Again, so this is written in resistive form rather than conductance, but yeah, your normal current contribution and your capacitive current contribution. So let's talk about the capacitive channel for a second. There's been some work recently. I don't know how or why, but many people have coalesced on this similar topic in the last year. I would argue we were the first to show the experiment, but there's been a lot of theoretical work in the last two or so years, just by chance. So Misaki and Nagaosa literally wrote a paper called The Theory of the Non-Reciprocal Josephson Effect, which seems quite apropos. And again, in this type of architecture, it's certainly a capacitor, and so you have a capacitance dependent upon, the usual, the permittivity and the area and all that. But the derivation of what could cause a non-reciprocal effect that they explain is that if you have an asymmetric charging, again, left does not charge the same as the right. So plus voltage charges the capacitor differently than minus voltage. If that happened, then you could end up with a delta, not IC, but they talk about a delta IR, the return current. So on the inside of the hysteresis. So that's interesting. And, oh, come on, computer. There we go. So, maybe we even see that. This wasn't that large, and I don't want to stress on it today because that's not the point of what I'm talking about, but it might be exactly that we're seeing. But the bottom line is this work and this theory didn't go through the delta IC, the breaking and onset of the superconductivity, not the return of it. So the outsides of the loops. So this explanation, at least this current explanation, doesn't explain our results. So for the moment, we're gonna drop that as well. So now we're left with supercurrent and the normal current contribution. Well, let's just really quickly tackle those. As I showed you guys earlier, we definitely do go to zero. We actually go to true zero resistance. So there is not a significant contribution from the normal current. It's all shunted through the supercurrent. So like we said already, it's not magnetochiral anisotropy for a variety of reasons. Even the geometry of what we've done is just wrong for even having a magnetochiral anisotropic effect. So that's not the driving factor. Also, just to throw this out there in case there were other arguments about NBSE2 being, a time reversal symmetry breaking superconductor on its own, that's just known not to be true, especially not in maybe the thick NBSE2. And niobium-3 bromine 8 is not known to be intrinsically time reversal symmetry breaking. Like I said, the work from earlier have pointed to a non-magnetic ground state, and certainly not a ferromagnetic ground state. And while some people predicted maybe in the monolayer these things could be maybe ferromagnets, that's not been shown or seen, and we're thicker than that anyway. So at the moment, there's no signs for this. So basically, we're left with the supercurrent. So, how do you get asymmetric tunneling with time reversal symmetry, but without inversion? Again, actually, Kitamura and Nagaosa, again in 2020, have thought about this, not in superconductivity, but in Landau-Zener tunneling. And again, it's a very great work, and I highly recommend everybody go read this wonderful paper. But to very, very oversimplify it, they basically propose that you can have a anisotropic, or I guess asymmetric probability for the tunneling, depending upon the shift vector generated by applying a magnetic field that depends upon essentially the band structure. So that is again a Landau-Zener picture, and that's not the type of tunneling we have. So maybe there's an analog with Andreev regime, but it hasn't been shown yet. It's again open work. Now, finally, one older work, actually, the first time I've actually seen anybody use the word Josephson diode, a great paper, proposed design of a Josephson diode by Jidai and friends back in the day in 2007. They actually had a very entertaining idea. They said, what if you take two high TC superconductors, you dope them so that their chemical potentials are different, like N-type and P-type, and then you smack them together, and you can end up with essentially a Mott insulating depletion region. So they're basically making an analog of a PN junction. And then they said the usual effects happen, and you have, the differing potentials for the, I guess, holons and doublons. Fine, whatever. The point is, you can end up with again a asymmetric tunneling. Now, is this what's happening? Do we have a Mott region or an internal polarization or some sort of wave packet shift? The bottom line is, what is the origin of our non-reciprocal behavior? We don't know. And I think that's the most fun. It's very exciting. It's not known. As I've hopefully tried to prove to you guys, we're positive the answer lies in asymmetric Josephson tunneling, not the other possible suspects. We're quite positive it requires the symmetry breaking, the inversion symmetry breaking. And we're quite positive it also requires an intrinsic property of the barrier material. In this case, I think you're going to see a work in the next year or 2 years at most on niobium-3 bromine-8 talking about it's gonna have some very interesting intrinsic properties that I'm sure some fancy theorists will explain in terms of some of the observations we had about why the heck does it have increasing conductivity as it goes thin. Is there some sort of non-trivial or even trivial surface state generated when you go thin? Is it something related to the inversion symmetry breaking? And does that correspond to polarization? Again, our experiments point in that direction. Let's see what theory says. In any case, it's an open question. How exactly does this work? I definitely proved it, but I don't know how it works. And the very fun thing is that there's a lot of other possibilities here, especially just the layered, let's say Kagome or layered hexagonal materials. Boy, there's a lot of different of property types that they can do. What happens if you make a quantum material Josephson junction out of a non-collinear magnet, or a quantum anomalous Hall insulator, or spin liquid, what have you? How did those intrinsic properties modulate the Josephson tunneling? I don't know. I didn't know this time, but look how it worked out. So yeah, this is now to just wrap up here, this is, the future. This is the direction we're trying to go. And this is, okay, now what we're going to be doing at Delft, actually. A large part of it is quantum material Josephson junctions. Again, like I said, the marriage of JJs and quantum materials is going to feed the future here. It's the next evolution of the Josephson junction. There's a lot of interesting things, lots of interesting properties, phenomena to be found. There are more and more layered quantum materials, which make this really quite easy. This was not that hard to do. There are a lot of more materials like that. There's the different classes of materials that should all maybe have fun results, maybe similar or maybe better, Maybe you can make a larger delta IC, or maybe there's, further modulation that can happen. Let's find out. Maybe you can incorporate strain into this game. And it's going to have an impact. Again, JJs are the basis for quantum computing today. Flat out, it is the basis for quantum computing today. Nothing has dethroned JJ-based quantum computing yet. Then there's quantum sensing, transduction. I've stolen these photos from the Delft website. But even, older things like latch logic and rapid single flux quantum computing. So related to that, there's one immediate application I'm just going to throw out there because I think we made a big impact, or we can make a big impact very quickly. And that's terahertz computing. Okay, so what do I mean by that? Superconductors, they switch very fast. This is very well known. It's very important and used in the detectors and various types of applications. How fast do they switch? I really mean fast, like on the terahertz scale, picosecond. Now, IBM obviously because they tried everything. IBM tried this. They tried basic JJ computing like 30, 40 years ago, and it didn't really pan out. And there's a few reasons, if you go and read the old papers about why, that are very entertaining. One of the things they explicitly say is that using underdamped JJs with hysteresis was a problem because they had to add extra current and energy, let's say, to overcome the hysteresis, to switch the different states. You know, if there's an extra hysteretic loop here, you literally have to add that much extra current. So that's not great. You want something non-hysteretic to be able to switch at lower energy easily. Fine. Well, we showed the Josephson diode behavior exists even in the non-hysteretic regime, right? I showed you that it worked even in the intermediately damped regime. Okay, what else? They specifically mentioned that IC, the critical current, had to be greater than like 100 microamps to ensure operation stability. Now, this is all at low temperature, okay? It's also down at the 2 Kelvin or so regime. It's not like they were doing this with high TC. It literally didn't exist at this time. They had not invented high TC yet or discovered it. So again, 100 microamps. Well, we've shown highly stable switching in the Josephson diode at, 10 microamps or less. And this is a little unusual actually, but I'm not going to talk about it today as to why, but basically it has to do with, the geometry and the thin layer and all that. So, okay, we solved that one. And then my favorite limitation they explicitly mention is that the clock frequency limitation of latch logic came from an undesirable effect of junction switching to the opposite resistant branch due to symmetrical IV curve, punch through error, right? And we've shown inherently that Josephson diode architecture resists punch through error because we have a delta IC. So, there you go, right? There's the several check marks. So I think we can revisit this right now. And I say, let's make a terahertz quantum material Josephson junction computer. Listen to that title, right? That should be $1 million from the European Research Commission, hopefully, right? Why not? Okay, so just to then wrap up, I have to acknowledge some wonderful people who've helped do all of this, particularly Professor Tyrel McQueen at Johns Hopkins. He has been the person who pioneered the materials of relevance here, and is just phenomenal. So if you ever, if you're interested in materials, go talk to Tyrel. Well, me as well, hopefully, but also Tyrel. He's just wonderful. He's a good friend. And then the postdoc who did all of this work, or primarily, also Dr. Yaojia Wang, but primarily the postdoc doing all this work was Heng, Dr. Heng Wu, who again did a phenomenal job. And if you find what I've talked about compelling, if you think this is interesting, then I am now hiring at Delft. I'm interested in graduate students and postdocs. So there's a lot of fun stuff to do, and I'm very, very serious about, proof of concept. Let's go start making that quantum material Josephson junction computer, Josephson computer, I'll call it that. And but alternatively, I'm always looking for collaborations, partnerships. Just shoot me an email. Always happy to discuss. So thank you very much for listening, and I'm happy to take questions now. How do I do that? Oh, how do we unmute somebody who's raised their hand?
Actually, I think I'm already unmuted.
All right, very good.
Muted myself.
Hi,
this is Niels speaking, from MPI Halle. Actually, I just have arrived as a new group leader at MPI Halle and now must leaving.
Sorry.
To Delft. Yeah. So I'm very jealous of you guys at Delft that you took him away from us so early. But I have to say, Maz, this is incredibly exciting stuff. I mean, I'm very impressed. I'm so impressed that I have to ask really nasty questions now.
For it. I love it.
Because I think, with results like those, the most obvious question, of course, is, what about reproducibility? Have you seen this in only one device, or have you seen this in multiple devices? What's the variation of delta IC, if you've seen it at multiple devices or not?
Right. So I'll try to reshare screen or, okay, anyways, very good question. And yeah, always super important. So like I said, I tortured my postdoc with exactly that, and made him go do it again and again and again, because, yeah, exactly. Is this really reproducible? And, you know, we'll probably be writing a paper in the future about the layer dependence with some more collaboration with theorists on that. But yeah, it's very reproducible. The delta IC tends to be in this regime of 0.2 to 0.5 or so microamps, well, 0.3 to 0.5 or so microamps. The IC, so it's interesting that the delta IC tends to be that large regardless of IC varying from, let's say, roughly 4 to 10 or, well, 4 to 8 microamps. So delta IC stays roughly the same, even though due to geometry purposes, you know, bigger, smaller, IC naturally changes as expected. And I think that's confusing and interesting and points more and more and more to the intrinsic, you know, effect of the barrier, right? That this is really something coming about not due to geometrical manipulation. So yeah, very, very good question. Sorry, so yeah, reproducibility, see other.
Yeah, just as a follow-up. So you're saying you've seen this in multiple devices, right?
Oh yeah.
And it was always 3 monolayers, or did you also try different numbers?
Right. So, yeah, that's a good point, and that's what I was alluding to. That we'll probably write something in the future related to the seeming layer dependence. But I guess to tease it, it's biggest. It looks biggest at 3, and we never got to 1. Okay, I'm just going to throw that out there. That, you know, to this day, somebody should make a mono layer. God knows what'll happen, regardless of Josephson. Maybe it'll be a ferromagnet. I don't know. Do it. We didn't get there, and I'm not sure we're going to continue on trying. You know, there's other cool things to try. There's too much to do. So 3 layers was the biggest effect, and it did seem to go, you know, away a bit as we got thicker. We're still trying to, you know, we'll eventually pin down and show something related to the really odd even, but it's a lot of work because you can't really control the layers until after you make it. I mean, you don't control it, rather, you just make it and then you go back and see how much did I make. It's not quite as Lego stacking as I implied yet. Yeah, there's a lot of fun to do. There's a lot to do as far as the layer dependence with this sort of thing. And I do encourage people to look at that.
Okay, thanks.
Okay, so I have another question here in the chat. Hopefully everybody can read it. I'll just read it out loud. Thanks for so Leo Peruchat says, thanks for the talk. You want to use these materials to realize a classical superconducting computer. What are the advantages, faster operations, dissipation? So related to what I was mentioning at the end, I think there are some advantages to realizing a classical superconducting computer in terms of a classical superconducting computer inherently is super fast, or can be super fast, if you can overcome certain issues of the latch logic, particularly how to switch back and forth. And basically that depended on being non-hysteretic and on not having punch through error. If you solve those 2 problems, which I think we did, then we don't know what the limit is, but it's certainly not on the order of gigahertz. It should be on the order of hundreds of gigahertz, back to the scale of this actual switching speed of the superconducting transition. So that's the advantage. Maybe there are disadvantages because at the moment, you know, this is proof of concept. I'm not saying yet that we can go and make a chip with, you know, 1 billion of these types of JJs on it. In fact, let's just do the math real quick. Okay, the typical semiconducting chip today has, I think, maybe 10 billion or so transistors, or is it trillion? I forgot. I think it's billion maybe. The point is, it's on the order of billions, but they're only on the order of gigahertz. So if I put 1 million JJs on a chip operating at 1 terahertz, you know, I'll reach an equivalence point almost, right? I'll get close. So can I make 1 million of these types of JJs on a chip yet? Oh no, I made one, right? Per sample. So that's in the future, okay? But you got to start somewhere. You know, you got to crawl before you can walk. So here we're just starting this, and there's a whole field. Is this really the right material to make a Josephson junction computer out of? Probably not. But it's the first time anyone's seen the Josephson diode effect. So someday somebody will figure out how to sputter, make this entire thing in a sputtered stack, and then you're off to the races. Okay. So that's the disadvantage for now, but you know, the future research direction. So thank you. Good question. Anton.
Yeah, thanks a lot for the talk. It is indeed really thought-provoking. So my question is also about something you alluded to, and specifically the frequencies. So since you're operating close to the instability regime, I was wondering if you have examined how things depend on the switching time, like if you push to higher frequencies or so, or measure the speed with which the switching happens.
Exactly.
Anything like that.
So yet we have not ramped up the speed, and that is something I really want to do, but we just don't have actually we don't have the electronics. I also tortured my postdoc, and I was like, go faster. But he literally just couldn't. Well, you know, we just don't have the right Keithleys basically and other things. So I really hope to do that at Delft in the very near future. I'm going to cart these devices over there and let's do it, because okay, how sharp is this? On the time scale of half a hertz, it looks infinitely sharp, but obviously that's not real. Again, superconducting transitions are by definition very, very fast, but we have not proven how fast this is yet. So I just don't have the data, but my speculation is that it should be. There's nothing here that should be slowing it down as far as I can tell, but boy, at the high speeds is where fun questions could be asked about, you know, is there a polarization? Is there a dipole? And is that dipole having to rotate? And can we reach the scale at which can we go fast enough that we don't let that dipole rotate before we switch polarity? And then what the hell happens? That's an even, other interesting question. Does it just stop? Or is there some very interesting intermediate regime? Some fluctuations or something. So as yet, we haven't pushed the limits of the frequency. We haven't pushed it at all, but that is the next step. That is the next direction to go. I just do want to point out, though, that at least in terms of temperature, we're not necessarily operating at the edge of instability. One nice thing about these devices with these materials, again, because we can go so thin, only 3 layers, the TC of the stack is almost just the TC of niobium diselenide, so quite high, like 6 Kelvin. Meaning we can easily park ourselves at like 2.5 Kelvin, which is well below the critical TC and not really at the edge of instability. So I showed this one here. I didn't actually show the lower temperature. Basically, it's only as we approach like 4 Kelvin that we start to see punch through air. And at very low temperatures, we absolutely don't. So at the 2 Kelvin regime, I think this thing is still going to be very stable. It's still like 3 or 4 times below the TC. And of course, just for stress testing purposes, if we test this at very low, dill fridge at 20 millikelvin, God, who knows? Let's see what happens.
So a quick follow-up question also, and that's related to ruling out the magnetization. And I understand it doesn't look likely, but just as a check, why? How can you be sure that you don't have out-of-plane magnetization? So I understand that you're applying the in-plane magnetic field, but maybe there is something finicky happening in the transverse direction, which is also, say, not due to either of the materials independently, but due to stacking. I'm not sure.
Yeah, I have a sneaking suspicion as well as with you that there is something like that, which is part of what 35 millitesla is related to, because this is an in-plane field applied. We have to be perpendicular to our current direction, right? For this whole effect. So yeah, this is an in-plane field and is 35 millitesla, you know, where something between some kind of out of plane to in-plane canting or something is happening. At this moment, we also don't know, but our collaborators in previous work have always argued that this material should not have any remaining magnetization, experimental work. It is only a theoretical work that, you know, is doing a low temperature ground state calculation that on the with the finite size effect on the monolayer that says maybe there's a ferromagnetism. But, you know, those things are, it's tough. It's tough to take that and say, yep, there's definitely magnetization, you know, in the 3-layer or whatever. Experimentally, there isn't any evidence yet, but this is part of why I'm trying to encourage people to go take a look at these materials. There's only like a handful of papers on niobium 3 chlorinate, niobium 3 brominate is even less, but I think it's overlooked. It's a super fascinating material, you know, but that's my usual game. I think I point out materials that maybe people didn't realize are as fascinating as they are, whatever. I think it's a very fascinating material and hopefully I'm proving it.
All right, thanks a lot.
Yeah, I think Niels had a question, or was it a real?
Actually, I had the same question as Anton about whether or not the few layer could be magnetic after all. So you're referring to this prior work, experimental work. Was that on the bulk material or also on the few layer?
Right, it's primarily bulk. Nobody has done like either local or very, very thin layer magnetization studies. I think everything was like above 100 nanometers. Even our previous work, which was on the conductivity, we got low. And we, in the normal, and that, oh, I should add that on, right? The previous work I was mentioning that we did as well on the thin flake in the normal state. So just using gold electrodes. We also tested, you know, magnetotransport, and we didn't see anything interesting at all, you know, down to, you know, the same, you know, millikelvin or whatever temperatures. But we didn't quite get to, you know, this same level of thickness. We got, I think, down to 5 nanometer, which was like, I guess that's roughly 10 layers or 8 layers or so. We didn't get to something like that. We didn't do the systematic all the way down to 3 yet. So we didn't see anything interesting in magnetotransport. And as far as I know, nobody's done, you know, the thin film local magnetization, which somebody should do now. Maybe that's, you know, maybe that comes back into play. Yeah, so, you know, there's open room. I'm happy to collaborate with people. Maybe that's something that can be done at Delft or outside, you know. I'm very happy to collaborate. I know Tyrel would be happy to collaborate on it. Also, there's another question here. I don't know if everyone can read it. So if we still have time for a short follow-up question, does delta IC have a specific direction, top to bottom or reverse in different devices? You know, actually, I don't quite remember which one was called negative and which one was called positive. Yeah, that's a good question. I don't think it had, let's say it was always, you know, negative, or let's say it was always, let's say, minus. So yeah, I don't think so. But I guess it would be interesting to go back and just double check, because I guess that could vary depending upon the extended architecture. But overall, I wouldn't expect that to, let me go back a few slides, or is this going to take a while? Okay. The devices are made, how do I say, relatively symmetrically, which is a funny thing to say at this time, in that there's always, you know, HBN, niobium diselenide, then our 3 layers, then niobium diselenide, then HBN, in that order. So there wasn't anything particularly special about, you know, up versus down in terms of a difference. So I don't think that is a factor, but, you know, here we go. Come on, yeah. But I could, if I could just get back to you about it. Oh, I think Niels is again asking a question. All right, Neil.
I mean, if no one else asks
Go for
questions,
it. Yeah.
there's time. So you were alluding to the fact that this may be a topological insulator or something like that.
Yeah. So in that paper, the topological quantum chemistry paper, they, I think it was Ben Weeder and friends had in their, that laundry list of compounds that were topological insulators or possible topological insulators based off of their calculations. Niobium 3-chlorine-8 was also included in that. Now, I don't know. It's never been proven. It's never been seen. And our let's see, where was it? Our conductivity experiment that I showed you, it does not point to it being a topological insulator, actually. So, and what I mean by that is that we don't see, oh, it's so terrible. Anyways, we don't see saturation at the quantum conductance level. It's much lower than that. So the quantum conductance should have been what, or in resistance, I guess, it should have been like 26 kilo ohm or something. We never reach that. We're always way more resistive. Even in our 5 nanometer or whatever device, we were still on the order of, I think, like 5,000, 2 or 3 orders of magnitude more, 1,000 times lower resistance. So we threw away the idea that this could actually be a topological insulator because we don't actually see surface state conduction at the quantum conductance level that we should have. So that, as far as we know, we're the only ones to actually have investigated that, and then we found that, not happy result. So yeah.
Right. But maybe there's some other, I don't know, origins of this higher resistance. Might still be, assuming that it is a TI or there are some surface states. Can that somehow explain what you see, assuming it's a spin polarized surface state?
What if it's, okay, just throwing this out there, and I know it sounds maybe a little bit stupid, but what if, there's some kind of surface state, and because we break inversion symmetry, like in WTE2, where various properties of the surface states don't have to be locked together. In that case, it was a Fermi velocity argument. Yeah, could something similar be happening here? Could there be, I think, what it looks like to me, based off of the diode effect and all that, and now I'm being in speculation mode, okay? Now this isn't in the paper, this is just us talking. It looks to me like there is a charge polarization almost. It looks like it's I would expect a ferroelectric barrier material to have this sort of behavior. I think for just relatively obvious reasons, right? So, because, then there's an internal field, an internal polarization. And if I apply a positive voltage versus negative voltage, it's either in the direction or fighting against, an internal E. So then maybe a similar delta IC should just naturally come out. So is this thing a ferroelectric? Probably not. Again, who knows? Nobody's ever seen it. Nobody's ever really talked about it. But there's no real reason to suspect it necessarily. The stuff that has been brought up is stuff about surface states. So could there be some sort of weird charge polarized surface state? I don't know. Like I said, I'm not a theorist, and I'm speculating, but if you're pushing me to speculate and just have fun, I'm throwing it out there, but don't hold me to it.
Okay, thanks so much.
Yeah, great. Thank you. Yeah, and somebody's asking, of course, my favorite question. The spatial supercurrent distribution from the Fraunhofer pattern. Yeah. So at the moment, I mean, it's only 3 layers thick. So here's the thing, right? You want to look at a spatial distribution of current over, I don't know, a couple nanometers, like it's a tough ask, okay? And you saw our Josephson Fraunhofer pattern. You can go inverse FFT that, and it'll look like you have current, you know, pretty much in this tiny area because your effective area is small. So it's hard to see. It's a good question, and it's a very relevant technique that actually I've used in a you know, literally our work on potassium vanadium antimony, another super popular now material, is playing the same game with spatial distribution of the current and the inverse FFT. But there, you know, we have it's planar, okay, and the magnetic field is out of plane. So the direction we're probing in terms of spatial mapping is the let's say left and right with the in plane, and that is on our microns. So then we are able to see like peaks, you know, at the edges, and then, you know, much smaller dense supercurrent density in the center of the sample. So it's basically that whole game is easier to see the bigger your channel is, and in our case that's just tough. It all looks like the same. It all just looks like there's supercurrent everywhere in your 3 nanometers or 2 nanometers or whatever. So, but good question. Good question. You're thinking in the right direction, but it's hard to do with insulating barriers because you have to go so thin. Okay. Neil, do you have another question, or is your hand still raised?
Yeah, sorry, my hand's no more questions. Thanks so much. Okay. Very impressive work.
Well, thank you very much. Well, like I said, this is, or maybe I didn't say, but it's under review right now at Nature. Fingers crossed. You know, everybody tells me it's impressive and good work. So I hope the referees agree. And if one of you guys are the referees, agree, please. Okay, let's go. Yeah. Okay, then I guess with that, I'll stop. Thank you all very much for listening. And like I said, I hope you found it interesting and compelling. And if you're interested in either collaborating or, you know, joining the group or being involved, let me know. Reach out. My emails are very easy to find on the internet. Okay?
Thanks a lot.
Okay, thank you guys very much. Bye, everybody.